Fine, let's start. Number 10. Rocks from the sky. For most of recorded history, if you told a scientist that rocks fall from space, they'd look at you the way you'd look at someone claiming their cat can do algebra. It was folklore. Peasant nonsense. The kind of thing uneducated farmers believed because they didn't know any better. The French Academy of Sciences, one of the most prestigious scientific bodies in Europe, went so far as to officially declare that stones cannot fall from the sky, because there are no stones in the sky. Hard to argue with that logic, honestly, and then, on April 26, 1803, the sky over Normandy, France disagreed. About 3,000 rocks rained down over the town of L'Aigle in broad daylight, in front of thousands of witnesses, not a handful of confused villagers, thousands of people. The French government sent physicist Jean-Baptiste Biot to investigate, and he came back with a conclusion that must have been deeply uncomfortable for a lot of people in very nice offices. The rocks came from space. Now, here's the part that stings. In the years leading up to L'Aigle, several European museums had gone through their collections and thrown out their meteorites, discarded them, because the scientific consensus said they were worthless folklore specimens, just ordinary rocks that superstitious people had attached stories to. Imagine being that curator. Imagine reading Biot's report and slowly realizing you chucked actual pieces of the solar system into a bin because the Academy told you to. Science is self-correcting, but sometimes the correction comes after you've already emptied the display case. Number 9, the moon is bone dry. When the Apollo astronauts brought lunar samples back to Earth, scientists studied them with everything they had, and the verdict was clear. The moon was dry. Not just dry, exceedingly dry. Drier than any desert on Earth. The samples showed no meaningful water content, and the chemistry suggested the moon had formed in conditions so hot and violent that any water would have been vaporized long before the surface cooled. Case closed. For 40 years, the moon has no water was one of those facts you could build a career on. It was in the textbooks. It was foundational. Except in 1978, Soviet scientists with the Luna 24 mission published a paper claiming they'd found traces of water in their own lunar samples. The paper appeared in a Russian journal called Geochemia. It was met with, let's call it, polite indifference. Western scientists largely ignored it. The water levels seemed implausibly high. The methodology was questioned. The finding quietly disappeared. 30 years later, India's Chandrayaan-1 spacecraft detected signs of hydration on the lunar surface. Then, NASA's L-Cross probe slammed into a crater and found water ice in the debris. Then, in 2020, NASA's SOFIA telescope, an infrared observatory mounted inside a Boeing 747, confirmed actual molecular water on the sunlit surface of the moon. Not ice hiding in shadows, water molecules baked into the dirt, sitting in plain sunlight. And in 2025, NASA researchers confirmed something that had first been hypothesized in the 1960s, that the solar wind, the stream of charged particles constantly blasting off the sun, smashes into the lunar surface and creates water through chemical reactions with the minerals in the soil. The sun itself is making water on the moon. A researcher involved in the study said, quote, "This decades-old idea about the solar wind turns out to be true. 40 years of certainty. One ignored Soviet paper and the sun quietly doing chemistry on the moon the entire time." Number 8, Mars and its canals. And in 1877, Italian astronomer Giovanni Schiaparelli pointed his telescope at Mars and mapped what he saw. He described long, thin features on the surface and called them canali. In Italian, that just means channels, natural grooves, nothing dramatic. But when the word crossed into English, it became canals, and canals are built by someone. Enter Percival Lowell, wealthy, passionate, and absolutely certain that the canals of Mars were the work of an intelligent civilization desperately irrigating a dying world. He built an entire observatory in Arizona, largely to study them. He wrote books, he drew detailed maps, he became famous. He was also wrong. The canals were optical illusions, artifacts of the human eye trying to connect scattered dark patches into lines. When the first spacecraft flew past Mars in the 1960s, there were no canals, no civilization. The whole thing collapsed into one of the most famous blunders in the history of astronomy. And that's where the story usually ends. Lowell was wrong. Everybody laughed, moving on. But here's the thing. Mars did have water, lots of it. Billions of years ago, the planet had rivers, lakes, possibly a northern ocean covering a significant fraction of the surface. In 2013, the Curiosity rover confirmed it was sitting inside an ancient lake bed in Gale Crater. In 2022, Perseverance found organic molecules embedded in the rocks of an ancient river delta. Lowell was wrong about the canals, wrong about the civilization, wrong about almost every specific claim he made, but his core intuition that water had shaped the surface of Mars turned out to be completely right. Sometimes the myth is wrong in every detail and true in its bones. Number 7. Professor Goddard doesn't understand basic physics. January 13th, 1920. The New York Times publishes an editorial titled "A Severe Strain on Credulity." The target, a physics professor at Clark University named Robert Goddard, who had published a paper suggesting that rockets could one day reach extreme altitudes, possibly even the moon. The Times was not kind. The editorial stated that Professor Goddard, quote, does not know the relation of action to reaction and of the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. Read that again. A newspaper told a physics professor he didn't understand Newton's third law. The implication was clear. Rockets can't work in space because there's nothing to push against. This was wrong. It was wrong when they printed it. Goddard had already proven in his own lab in 1916 that rockets generate thrust perfectly well in a vacuum. The exhaust pushes backward, the rocket moves forward. That's it. That's Newton's third law. The medium doesn't matter, but the damage was done. Goddard became a target of public ridicule. He was nicknamed Moon Man. He grew secretive, moved his research to Roswell, New Mexico, and spent the rest of his career working in near isolation, largely funded by a single grant secured with the help of Charles Lindbergh. He died in 1945. He never saw the space age he made possible. Now fast forward to July 17th, 1969, the day after Apollo 11 launched for the moon. The New York Times published a short item under the headline, "A Correction," 3 paragraphs. It summarized the 1920 editorial and concluded, "Further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum as well as in an atmosphere. The Times regrets the error." The correction never mentions Apollo 11, not once. 3 astronauts are already on their way to the moon aboard a Saturn V rocket-burning liquid fuel, exactly the kind of propulsion Goddard pioneered, and the paper of record just quietly notes that, yes, Newton was right after all. 49 years, the greatest understatement in the history of American journalism. Number 6, the afterglow they mistook for bird droppings. In 1948, physicists George Gamow, Ralph Alpher, and Robert Herman made a prediction. If the Big Bang actually happened, if the universe really did begin in an incomprehensibly hot, dense state and has been expanding ever since, then there should be leftover radiation from that initial fireball. A faint glow cooled over billions of years to just a few degrees above absolute zero, filling every corner of the cosmos. An afterglow of creation, it was an elegant prediction, and almost nobody paid attention to it. The paper was published, cited a few times, and then more or less forgotten. 17 years later, in 1965, 2 radio engineers at Bell Telephone Laboratories in New Jersey were trying to calibrate a large horn antenna. Arno Penzias and Robert Wilson kept picking up a persistent low-level noise they couldn't eliminate. It was the same in every direction. It didn't come from the city, it didn't come from the atmosphere, it didn't come from the galaxy. They checked the equipment, they rebuilt connections, they found pigeons nesting inside the horn and cleaned out what Wilson later diplomatically described as a white dielectric material. In other words, bird droppings. Wilson would later say the cleanup did knock a little bit off our measured temperature. There was some radiation from the bird droppings. But the noise remained. They were on the verge of publishing it as unexplained interference when a colleague mentioned that a group of physicists at Princeton, just 40 miles away, had been building their own antenna to search for exactly this kind of signal. Penzias and Wilson suddenly realized they hadn't found a problem with their equipment. They'd found the edge of the observable universe. What they were hearing was the cosmic microwave background, the afterglow of the Big Bang, stretched by 13.8 billion years of expansion into faint microwave radiation with a temperature of 2.7 degrees above absolute zero. It is the oldest light in the universe. Penzias and Wilson won the Nobel Prize in 1978. Gamow, Alpher, and Hermann, the physicists who actually predicted the radiation, did not. Gamow had died in 1968. Alpher spent decades feeling the injustice. The fingerprint of creation was picked up by an antenna built for telephone signals and initially blamed on pigeons. The people who found it got the prize. The people who knew what it would sound like did not. The universe has a sense of humor, but it's pretty dry. Number 5. An asteroid killed the dinosaurs and nobody believed it. In 1977, geologist Walter Alvarez was collecting limestone samples near the small Italian town of Gubbio. Between two layers of rock, one from the Cretaceous period, one from the Paleogene, he found a thin band of reddish clay. Below the clay, the limestone was packed with tiny marine fossils. Above it, almost nothing. Something had killed most of the life in the ocean right at that boundary. Walter brought the samples to his father, Luis Alvarez, a Nobel Prize-winning physicist at Berkeley. Luis suggested testing the clay for iridium, a metal rare on Earth but common in asteroids. The results came back 600 times above normal levels. In 1980, the Alvarezes and their colleagues Frank Asaro and Helen Michel published their hypothesis in Science. A massive asteroid, roughly 10 kilometers wide, had struck the Earth 66 million years ago, throwing enough dust and debris into the atmosphere to block sunlight for years, collapse food chains, and wipe out 75% of all species, including every non-avian dinosaur. The geology community did not take this well. For decades, the dominant view in geology had been uniformitarianism, the idea that Earth changes gradually through slow processes over immense timescales, the notion that a single catastrophic event could reshape the entire biosphere felt like a throwback to pre-scientific thinking. The Alvarez hypothesis was resisted, mocked, and aggressively challenged. Paleontologists pointed to gaps in the fossil record. Volcanologists argued that massive eruptions in India, the Deccan Traps, were a better explanation. Over 2,000 papers were published in the 1980s debating the question. Then, in 1991, the smoking gun appeared. Geophysicists identified a crater buried beneath sediment on the Yucatan Peninsula in Mexico, 180 kilometers wide, 25 kilometers deep. It had actually been drilled into by oil prospectors back in 1951, but they dismissed it as a lava dome, a feature uncharacteristic of the region's geology, sitting there for 40 years, misidentified. The geophysicist who helped identify it partly chose the name Chicxulub, after a nearby town, because, as he later admitted, he wanted to give the academics and NASA naysayers a challenging time pronouncing it. That's a level of petty I deeply respect. In 2010, an international panel of 41 scientists reviewed 20 years of evidence and ruled the Chicxulub impact was the primary cause of the mass extinction. The Alvarezes were right. The evidence had been sitting in a thin band of clay in an Italian hillside and in a drill core from the Yucatan that nobody looked at twice. The end of the dinosaurs was written in iridium dust and buried under 40 years of scientific resistance. Number 4. The priest who explained the universe and got told his physics was atrocious. Georges Lemaitre was a Belgian Catholic priest. He was also a physicist trained at Cambridge, Harvard, and MIT, with a deep command of Einstein's general relativity. In 1927, he published a paper arguing that the universe is expanding, that the distance between galaxies is growing over time, and that if you run the clock backward, everything converges to a single point. A primeval atom, he called it. A cosmic egg. Einstein read the paper. They met at a conference, and Einstein told Lemaitre to his face, "Your calculations are correct, but your physics is atrocious." Think about that for a moment. The math checks out, but I don't like the conclusions. So I'm going to call your physics atrocious. That's not a rebuttal. That's a feeling. 2 years later, Edwin Hubble published observations showing that distant galaxies are indeed moving away from us and that farther galaxies are receding faster. The universe was expanding exactly as Lemaitre had calculated. Einstein changed his mind by 1931, but the resistance didn't end there. British astronomer Fred Hoyle championed a rival idea, the steady-state model in which the universe has no beginning, no end, and continuously creates new matter to fill the gaps left by expansion. During a BBC radio broadcast on March 28, 1949, Hoyle dismissed Lemaitre's theory with a phrase, "this idea that everything began in one big bang." He meant it as mockery. The name stuck. The most successful theory in the history of cosmology is still called by the insult its biggest critic gave it. Hoyle never accepted the Big Bang. He fought against it until he died in 2001. And then there's the final layer. When Einstein first formulated general relativity, he realized his equations predicted a universe that was either expanding or contracting. But everyone, Einstein included, assumed the universe was static and eternal. So he added a fudge factor, the cosmological constant, a repulsive force that balanced gravity and kept everything in place. When Hubble proved the universe was expanding, Einstein dropped the constant. He reportedly called it his biggest blunder. Then, in 1998, 2 teams studying distant supernovae made an astonishing discovery. The expansion of the universe isn't just continuing, it's accelerating. Something is pushing galaxies apart faster and faster. Physicists call it dark energy, and it makes up roughly 68% of everything that exists. And the best mathematical description of dark energy looks remarkably like Einstein's discarded cosmological constant. He added it for the wrong reason. He removed it because he thought it was a mistake. And it turned out to describe the dominant force shaping the fate of the cosmos. A priest proposed the beginning of everything. Einstein called it atrocious. A rival named it as a joke, and the man who got the closest to the full picture was wrong about being right. The universe doesn't care about your credentials. It just is what it is. Number 3, trillions of homeless worlds. There's a particular kind of science fiction image that's hard to shake. A planet drifting through deep space, no star, no system, just a dark world tumbling through the void in perfect silence. It feels like a horror movie premise, or a metaphor for loneliness. Turns out it's just astronomy. The first hints of free-floating planets, rogue planets as they're now called, appeared around the year 2000. Faint infrared signatures in star-forming regions that didn't seem attached to any star. The detections were tentative. The objects could have been very dim, failed stars, not planets at all. For years, they remained in a kind of scientific limbo. Interesting, but unconfirmed. Then, in December 2021, astronomers found at least 70 of them in a single region of space. The Upper Scorpius Stellar Association, about 400 light-years from Earth. Not 1 or 2 anomalies, 70. Possibly as many as 170. And on January 1st, 2026, literally the first issue of Science published that year, A team led by researchers at Peking University reported the first direct mass measurement of a rogue planet. A Saturn-sized world drifting through space roughly 10,000 light-years away, orbiting nothing. Hey, the mass wasn't estimated or inferred from statistical models. It was measured directly using simultaneous observations from ground-based telescopes and the European Space Agency's Gaia satellite. Professor Andrei Udalski, leader of the OGL project that contributed to the discovery, called it the discovery of the decade, comparable to the discovery of the first documented extrasolar planets in the 1990s. And here's where the scale gets strange. Theoretical models suggest there may be several times more rogue planets than stars in the Milky Way. Not a few oddities, billions, possibly trillions, dark worlds, sunless, drifting in silence through interstellar space. Most were probably born in normal planetary systems and then flung out by gravitational chaos, close encounters with larger planets, unstable orbits, the slow violence of celestial mechanics. Some models suggest that rogue planets with thick atmospheres or subsurface oceans could retain enough internal heat to keep water liquid beneath a shell of ice. No sunlight, no surface, just a dark ocean under kilometers of frozen crust, heated from within, drifting between the stars. We may live in a galaxy where the number of sunless worlds with hidden oceans vastly exceeds the number of stars in the sky. No light, no orbit, no dawn, just water and warmth and silence for billions of years. Cricket. Number 2, the boy who was laughed out of the room. In 1930, a 19-year-old student named Subramanian Chandrasekhar boarded a ship in Madras, India, bound for Cambridge, England. He'd won a scholarship to study astrophysics. He'd already graduated from Presidency College, and during the long voyage, with nothing but time and a notebook, he started working through the equations describing what happens to a star when it runs out of fuel. The accepted understanding at the time was straightforward. When a star dies, gravity compresses it into a white dwarf, a dense, cooling remnant roughly the size of Earth. Ralph Fowler had recently shown that quantum mechanical pressure from electrons would halt the collapse. Every star, no matter how massive, would end the same way. Chandrasekhar found a problem when he applied both quantum mechanics and special relativity to the equations, something nobody had done together before. The math said there was a limit. Below about 1.4 times the mass of the Sun, yes, the electron pressure holds, the star becomes a white dwarf. Fine. But above that limit, the pressure fails. The electrons can't hold, gravity wins, and the star doesn't just shrink into a white dwarf, like, it collapses into something else. Something the physics of the time had no name for. He arrived in England and began refining his calculations. Over the next 4 years, he worked closely with the most distinguished astronomer in the world, Sir Arthur Eddington, the man who had confirmed Einstein's general relativity in 1919. Eddington checked in regularly on Chandrasekhar's progress. He seemed interested, supportive even. On January 11th, 1935, Chandrasekhar was invited to present his findings at a meeting of the Royal Astronomical Society. Eddington arranged for him to have double the customary 15 minutes. What Chandrasekhar didn't know was that Eddington had also scheduled himself to speak immediately afterward, and had told no one what he planned to say. Chandrasekhar presented his full solution: a mass limit for white dwarfs. Above it, collapse. Below it, stability. The math was rigorous. Then Eddington stood up, and rather than engaging with the mathematics, he ridiculed the conclusion. He called it physically meaningless. He argued that combining quantum theory with relativity in this way was untenable. He dismissed the entire framework. The room sided with Eddington almost unanimously. He was the most famous scientist in British astronomy. Chandrasekhar was 24 years old from colonial India and had just been told, in front of every major figure in his field, that his life's work was nonsense. Chandrasekhar later recalled the moment. The lack of approval by one's contemporaries can have tragic consequences when they are expressed in the form of sharp and violent criticisms. Einstein himself published a paper in 1939 attempting to prove that the kind of total gravitational collapse Chandrasekhar described, what we would later call a black hole, was physically impossible. Einstein was wrong. But here's the detail that haunts this story. Eddington's own argument against the Chandrasekhar limit included a description of what would happen if the limit were real: a star collapsing beyond all known physics, shrinking past any possible equilibrium, falling inward without end. He described a black hole in the process of arguing that black holes can't exist. He saw the answer and called it absurd. Chandrasekhar, devastated, left the United Kingdom in 1937. He moved to the University of Chicago, where he spent nearly 60 years making contributions across half a dozen fields of astrophysics. He didn't just survive the humiliation, he outgrew it. In 1972, the first black hole, Cygnus X1, was detected. In 1983, Chandrasekhar won the Nobel Prize in Physics. In 2019, the Event Horizon Telescope produced the first direct image of a black hole, a glowing ring of superheated gas around an absence, a shadow in the shape of exactly what a 24-year-old calculated on a ship from Madras. Eddington died in 1944. He never retracted his criticism. The objects Chandrasekhar predicted are now the most studied, most mysterious, and most extreme things in the known universe. And every one of them sits above a line drawn by a teenager on a boat, a line the entire establishment told him didn't exist. Number 1. Ripples in the fabric of reality. In 1915, Albert Einstein published his general theory of relativity. It described gravity not as a force pulling objects together, but as the warping of space-time itself. Mass bends the fabric of the universe and other objects follow the curves. It was elegant, it was radical, and within a year, Einstein realized his equations predicted something even stranger. If massive objects warp spacetime, then massive objects in motion, two stars orbiting each other, two black holes spiraling inward, should send ripples outward through that fabric. Gravitational waves, literal tremors in the structure of reality, propagating at the speed of light. Einstein published the prediction in 1916, and then almost immediately he began to doubt it. The distortions would be unimaginably small. Even the most violent events in the cosmos, colliding neutron stars, merging black holes, would produce ripples that, by the time they reached Earth, would stretch and compress space by less than the diameter of a subatomic particle. Einstein concluded they were a mathematical curiosity, real perhaps, but effectively invisible, unmeasurable, a prediction that could never be tested. For decades, most physicists agreed. Gravitational waves were a footnote, theoretically interesting, practically irrelevant. In 1974, Russell Hulse and Joseph Taylor found indirect evidence, a pair of neutron stars whose orbit was decaying in exactly the way it would if they were losing energy to gravitational waves. They won the Nobel Prize in 1993, but nobody had felt a wave directly. Nobody had built a machine that could. Then someone tried. In the 1980s, physicists Rainer Weiss, Kip Thorne, and Ronald Drever proposed an audacious instrument. Two L-shaped detectors, each with arms 4 kilometers long, placed thousands of kilometers apart. One in Livingston, Louisiana, one in Hanford, Washington. Inside the arms, laser beams would bounce between mirrors hanging in near perfect vacuum. If a gravitational wave passed through, it would stretch one arm and compress the other by an almost inconceivable amount. The instrument would need to detect a change in length smaller than 1/10,000th the diameter of a proton. The project was called LIGO, the Laser Interferometer Gravitational Wave Observatory. It took years to fund, years to build, years to upgrade. The original detectors, operational from 2002 to 2010, found nothing. Not a single event. The instruments were rebuilt with improved sensitivity, advanced LIGO, and brought back online in 2015. On September 14th, 2015 at 5:51 in the morning Eastern Time, both detectors registered a signal, a rising tone lasting a fraction of a second, a chirp. The waveform matched almost perfectly the prediction from general relativity for two black holes, one 36 times the mass of our sun, the other 29, spiraling into each other and merging into a single larger black hole 1.3 billion years ago. In the final fraction of a second before they merged, those two black holes were orbiting each other at nearly half the speed of light. The collision converted roughly 3 solar masses worth of matter into pure energy, released as gravitational waves. For a brief instant, that single event radiated more energy than every star in the observable universe combined. That energy rippled outward through space-time for 1.3 billion years. It passed through galaxies, through the voids between galaxy clusters, through the Milky Way, through our solar system. And when it reached Louisiana, it briefly made one arm of the LIGO detector about 4 thousandths of a proton wider than the other, and we caught it. The signal arrived during an engineering test run. The formal science observations hadn't even officially started yet. LIGO had spent over a decade listening to silence, and the universe spoke during a sound check. The detection was announced on February 11th, 2016. Weiss, Thorne, and Barry Barish-Gourpre, who had led the project to completion, shared the Nobel Prize in 2017. Here's what stays with me about this one. It's not just that gravitational waves are real. That was always the safe bet. Einstein's math is very good. It's that for 100 years, the consensus was that we'd never be able to prove it. The waves were too faint. The technology was impossible. The precision required was absurd. And yet, a small group of physicists spent their entire careers building a machine sensitive enough to measure a distance smaller than a fraction of a proton, and they pointed it at the sky and they waited. For over a decade, they waited. And then, one morning, while they weren't even officially looking, the universe handed them a signal from 1 billion years ago. 2 black holes annihilating each other in a collision so powerful, it shook the geometry of space itself. The myth was never that gravitational waves exist. Einstein knew they did. The myth was that the universe keeps its deepest secrets locked away forever, that some truths are too faint to reach us. They're not. We just had to build a machine quiet enough to listen. And here's the broader thing, the thread that runs through every item on this list. A newspaper said rockets can't work in space. The most famous astronomer alive said, black holes are impossible. Einstein said, the universe isn't expanding. The geology establishment said, catastrophes don't happen. The Apollo program said, the moon is dry. And for decades, in each case, the consensus held, until it didn't. The lesson isn't that scientists are usually wrong. They're not. The scientific method is the best system we've ever built for figuring out what's true. But the universe doesn't care about consensus. It doesn't wait for peer review. It doesn't adjust itself to match the prevailing model. It just sits there, being what it is, until someone stubborn enough or lucky enough or young enough to not know better comes along and sees it clearly. The next myth waiting to be proven true might already be sitting in someone's rejected paper, or in a data set nobody's looked at closely enough, or in an observation that doesn't quite fit the model that everyone's agreed to quietly ignore because the alternative is too strange. The universe is under no obligation to make sense to us. But every now and then, when we build the right instrument, or ask the right question, or just refuse to throw out the rocks, it lets us in on the joke. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.